that simply it is about valency changes in groups and periods. Last topic in yesterday's class about the changes of valency in groups and in periods. So here simply periodic classification or periodic table classification based on a electronic configuration, right? So don't forget this electronic configuration. So here similar electronic configuration is there, right? Similar electronic configuration is there in a group and in periods. That electronic configuration changed by 1 unit in periods. So this you need to keep in mind. If you know this point, very easy to understand about valency. Right? So here, what is valency? Combining capacity. Why they are combining? Simply to get octet configuration. Right? Octet configuration. So left their electronic valence shell electrons with 8. So if they attains 8 electrons in the valence shell, automatically that becomes stable in a chemical reaction, but do not participate. So that we can quantize, here simply octet configuration. So for that, they are participating in the chemical reaction. So depending on the valence expression, right? Number of electrons present in the last shell. So that we can call it as valence shell electrons, right? So here, how many required to get octet configuration, or how many are there more octet configuration? So that may be lose or gain. So in the group, there are with similar electron configuration. So valency remains same in the group. In the periods, valency not following regular tendency, because every time one electron added to the valency shell. So valency not following the regular gradation in a period. Right? So this is you need to understand in a groups and a periods. So valency identification is very easy in a group. Right? So here 1 to 4th group, it is given just simply its group number is valency number. Right? Valency for 1A group is 1, 2A group is 2, 3A group is 3, 4A group is 4. Then from 5th group onwards, just you are following one simple logic, subtracting the group number from 8. So 8 minus 5, group number 5, 8 minus 5, that is giving you 3. 3 is the valency of group 5A. Like that you are finding. So this is also one of the easy techniques for finding the valency. So this is applicable for especially S and P block elements. Then now our topic is about here simply atomic radius, or also called as atomic size. Right? So here in a Bohr's atomic model, we learned about electrons revolving around the nucleus in fixed orbits. Right? So fixed boundary is there for moving electrons around the nucleus. Fixed boundary is size from where to center on nucleus to the outermost shell. What is the last shell is available? So that shell you are measuring the distance. That distance is called as here outermost shell. Right? Outermost shell distance from the nucleus. That is called here atomic radius or atomic size. Right? So here simple. For example, if you take any atom, let me take suppose calcium here. So it is its nucleus. Right? This is the nucleus. Then how many shells are needed to fill it? Calcium atomic number is 20. So distribution of electrons into the K shell, 2, right? K shell, 2, L shell, 8, M shell, 8, and N shell, 2. So how many shells? Nearly 4 shells. So that 4 shells we are taking around the nucleus. So first shell, second shell, third shell, and fourth shell. Right? So 4 shells are taken here. Then distribution of electrons taking place into this. So where the differentiating electron is located in the calcium atom? Can anybody answer? Differentiating electron. Where the differentiating electron is available? In which shell? Shells are here named as here K shell, L shell, M shell, and N shell. So 4 shells are available where the differentiating electron is available in the calcium atom. So that is available in the N shell. So 2 electrons into the K shell, 8 electrons into the L shell, 8 electrons into the M shell. So up to here, how many? 18 completed. 2 more left. They are in a N shell. So here you are measuring simply the distance from the nucleus to the outermost shell. So which is outermost shell? It is N shell. So this distance is called atomic radius. The distance from the nucleus to the valency shell, outermost shell is called valency. So are you clear about this one? How you are measuring the atomic radius? What is called as atomic radius? Is it clear? Right. So now, what are the units we can assign for the atomic radius? Right. So actually, atomic size is very smaller. Atomic size is very smaller. That atomic size we are measuring in meters. That is negative powers, picometer. So here atomic radius is measured in picometers. So here atomic radius named differently. Suppose if you are measuring the atomic radius of metals, right? Atomic radius of metals, that atomic radius is called as metallic radius. Right? Atomic radius of metals called as atomic radius, metallic radius. Right? Then here units of this metallic atomic radius is equal to 10 to the power of minus 12 meters called 1 picometer. 1 picometer. Sometimes you may express these as nanometers also. In nanometers, 1 nanometer is equal to 10 to the power of minus 9 meters. Sometimes that is maybe given in angstrom units. 1 angstrom unit is equal to 10 to the power of minus 8 negative power. Right? So 1 angstrom unit equal to 10 to the power of minus 8 meters. So can you convert these angstrom unit into nanometers? Angstrom unit into nanometers? Yes, we are able to convert. So here I know 1 angstrom is equals to 10 to the power of minus 8 meters. So this one I am changing like this. Right? So 10 by 10. Any difference is there? Any difference is there in the value? No difference. So here this denominator will be written as 10 power minus 1 in the numerator. Any difference now? No difference. So what I am doing here, adding these negative power. So 10 to the power of minus 8 and 10 power minus 1 added together, we are getting minus 9 meters into 10. So what we will write? So 10 into 10 to the power of minus 9 is taken as nano. So 10x, 10 nanometers. 1 angstrom equal to 10 nanometers. also we can convert. Are you clear about this value conversion? Is it clear? Converting angstrom units into nanometer. Right? Now, here, look at this one. Can you name this atom? What it is? Can you name this atom? Name the atom, please. How many number of electrons are there? Name the atom. You have unmute option, I think. So count the number of electrons. Here, 2 available in the first shell, K shell, right? 2 electrons. Next, second shell completely filled, 8. Third shell having 8. Then last shell, 1. So totally 16 plus 3, 19. This is 19th element simply. What it is? Potassium. What is potassium? So atomic radii is measured from nucleus to the outermost shell is SKLMN, nth shell. So this is radius, right? So radius is measured in a picometer. Radius is measured in picometers. K shell filled with 2 electrons, L shell filled with 8 electrons, M shell filled with 8 electrons, and N shell has 1 electron. So from the nucleus to the outermost shell, nth shell, called this is atomic radius, size of the potassium element of atom. This is about atomic radius. For example, here one more atom is taken. Can you name the atom, please? Here, what is the atom? What is the atom? Here, K shell, 2, M shell, L shell, 8, M shell, also 8. So totally 18. So 18th element, that is argon. So now look at the atomic size of this atom. Atomic size of this atom. K shell only 2, L shell 8, M shell 8. So from nucleus to the outermost shell is what? M. That is atomic radius. Can you compare the atomic size of these two elements? These two elements, potassium and argon. Which has greater atomic size? Which has greater atomic size? And why? Answer me. Answer me. What is the difference in these both atoms? Is there any difference in the atomic sizes? Why you got this difference? No one responding. Teacher,
Sir,
what happened? Everyone silent.
sir, observing.
Observing. Okay. Give me answer. What is the difference? Is there any difference of their atomic sizes?
Yes, sir.
Which has greater atomic size and why?
Sir, potassium has greater atomic size.
Reason?
Sir, me, Srichar.
See the number of shells count around that. Number of shells. How many? 1, 2, 3 shells are there. Why you required more number of shells for potassium? Because atomic number is increasing. As the atomic number increasing, you require more number of shells to arrange the electrons. To distribute the electrons, you require more number of shells. So this is the difference, right? So look at here, simply atomic radius or atomic size varies in the groups and in the periods. Why it changes? Why not it remains same atomic size? Atomic size is what? Simply the distance between the nucleus to the outermost shell. So number of shells depending on what? Atomic number, right? So atomic number is constant for every element? No, it is changing, right? So as the atomic number changing, electron distribution of electrons also changes into the various shells. So as the atomic number is increasing, number of shells also increasing. Number of shells also increasing. So number of shells increases, atomic size automatically increases. So within the group, from one element to another element, extra shells are added. Extra shells are added. So as the extra shells are added, automatically atomic size increases from top to bottom. For example, hydrogen, it has only one shell as main shell, that is K. Next, lithium, it has main shells to sodium, main shells K, L and M, 3 shells. If you go to potassium, 4 shells K, L, M, N. Have you following? Are you following? Is it clear? Is it clear? So as the number of shells increasing from top of the element in the group to the bottom of the element, what's happening? Every time an extra shell is going to be added to distribute the more number of electrons you require that. Right? So this is the reason to increase atomic size within the group from top to bottom. From top to bottom. So look at here. Here, going to down in the group from top to bottom. So every time you are required more number of shells to distribute the electrons. So as we go down in a group, atomic number increases. According to it, number of shells increases in a group from top to bottom. So this is the reason for finding the greater atomic size from the bottom element. Right? The top element with less atomic size, bottom element with greater atomic size. Look at here. I am taking one of the elements. So which element is this? Which element is this? Helium. So it is having only 2 electrons. They are in the cation. Right? So next element I am taking here. For example, here 2 electrons distributed into the first shell. Then one more electron I am distributing into second shell. So what it may be? Lithium. Right? Lithium. So which has greater atomic size here? Among the 2 elements, which has greater atomic size? Helium or the lithium? Helium or the lithium? Anyone? Helium or the lithium? What happened?
Lithium, sir.
Lithium. So lithium has greater atomic size. Due to what reason? Can you guess the reason for this? Here you are able to understand 2 things. One is about the number of electrons and the number of shells. So only it is increased by 1 electron. Lithium increased by one electron, atomic number increased by 1 unit, pairing with the helium. But to fill that one electron, you are required one more shell. So as the number of shells increased, automatically atomic size increased. That is the distance from the nucleus to the outermost shell. So this is the variation in the group. The next here, that variation in periods. So atomic number is increased within the periods as we move from left to the right. For example, here lithium. Lithium atomic number is 3. Next, immediate element is beryllium. It has atomic number 4. Boron, atomic number is 5. Carbon, atomic number is 6. Nitrogen, 7. Oxygen, 8. Fluorine, 9. And neon, 10. So here, can you observe the outermost shell for these elements? So here, first shell, second shell. To distribute 3 electrons. Okay. Then beryllium. Right. So for beryllium, how many shells are required? Only 2 shells enough. So 2 electrons into the K shell, then 2 more electrons into the L shell. Next, boron. How many shells are required? 2 shells are enough. So maximum capacity of third shell is 8. So 3 distributed. Then next about it is carbon. How many are required? 2 into the main shell. Okay. Next, how many? 4 into the main shell L. Next, nitrogen. For nitrogen, 2 is enough. So 2 into N shell. Next, 5 into L shell. Next, fluorine. For fluorine also you are required same number of shells. There is no difference in the count because the maximum capacity of L shell is 8. You are just left with 6. Sorry, 7. 2, 3, 5, 2, 4, 6, 2, 5, 7, and 2, 6. Okay, the next about neon here I am writing 2 into the first shell and 8 into the next. If there is any mistake in the count of electrons, you can modify. 3 plus 4, okay, 8. So look at what is commonly observing in this. What you are observing commonly? Number of shells are same. Is there any change in that number of shells count? Is there any change? No. K shell and L shell. No difference in that. So here within the period, within the same period, you are distributing the electrons into the same shell. Is there any change in the valency shell? Observe carefully. Answer me. Respond. What is valency shell for each element? Same or different shell? It is same shell, L shell. So no change in the shell. Right? Then what happened? If you observe carefully, 3, 4, 5, 6, 7, 8, 9, and 10. So proton count is changed. Proton count is changed, increased. Right? Proton count is increases from left to right within the same period. So as the proton count increases, we can say that as nuclear charge is increased. Nuclear charge is increased. What is nuclear charge here? What number of positive charges considered in the nucleus? So that charge is considered to be nuclear charge. So charged particles only positive charges inside the nucleus. Neutrons, neutral, and other particles present inside the atom considered to be chargeless. So only protons are positively charged particles, that is considered to be nuclear charge. Okay. So here, as we move from left to right, positive charge is increasing on the same valency shell. On the same valency shell. So here, as the nuclear charge increases, what happens? That electrons come closer to the nucleus because of greater attraction force by the nucleus. How the greater attraction force is available? Because increasing in the atomic number. Increasing in the atomic number. So that all the proton attraction power on the same valence. So that is the reason to get that the size is small. So when you move from left to right, here that atomic size is decreasing because that electrons are entering into the same valency shell. Same valency shell. So this is you are closely observing in this. So number of shells are and same and the distribution of electrons into the same shell automatically atomic size decrease due to increase in the nuclear charge. Right? Nuclear attraction force. So as you move away from the nucleus, what happens? That electrons entering into the inner cells again. D block and F block. Right? D block and F block. So in that case, again that atomic size is decreasing. Right? So atomic size within the period, as we move from left to right, decreases. Within the groups, increases. See, opposite V. That characteristic property is changing. In groups, top to bottom, increase in atomic size. But in the period, left to right, the same atomic size decreasing. Right? So this you need to concentrate. The next about atomic size variation based on the atomic charge, nuclear charge, maybe positive charge or negative charge, by losing or gaining the electrons. So losing of electrons will give you positive charge, gaining of electrons will give you negative charge. So atomic size also depending on what charge of the atom. So here simply positive ion of an element, positive ion of an element has size greater than or less than to the neutral atom. What it has? Less size. Right? It has less size. Why it has less size? Why it is becomes smaller while losing the electrons? For example, here I am taking sodium atom as example here. So what is the number of sodium atomic number?
11.
11. So distribution of electrons into the shell. How many shells are needed? You require here 3 shells. 2 plus 8 plus. Right? So 2 and 8 into the main shell, K shell, and the next shell is M shell. K, L shell. So 8 are distributed. Then one more electron you need to distribute, that is into the outermost shell is L shell. So distributed. So sodium atom has something size. From nucleus, right? From nucleus to the valence shell, M shell. Right? Then if I remove one electron from the valence shell, I am going to remove the electron. So electron is removed. Look at here. Last electron, here it is located. That electron I am going to remove from the valence shell. What happens when I remove the electron? So up to where you are measuring the size, electron is available. Electron is located in the third shell? No, not located. So no importance for the third shell also here. So So it is became Na plus. Atom became ion. As positive ion. So Na plus has 11 protons, 10 electrons. Na plus has 11 protons, but the electrons count is only 10 because one electron is removed. So no importance for the valency shell M here. So which became as valency shell here after removing one electron? That is here simply it is M shell. So the distance you are measuring here from nucleus to the L shell. So M shell greater distance, L shell less distance comparing with that. So Na plus has less atomic size comparing with Na atom. Right? Na plus has less atomic size comparing with Na atom. So that size also measured in picometers given here. So Na plus atom 98 picometers, sodium atom 157 picometers. Which has greater size? Is it atom or the ion? Which has greater atomic size? Atom or the ion? Atom. So similarly, you are able to measure the atomic size of negative ion. For example, here chlorine is considering. Right? The negative ion of an element has bigger size. Ion has bigger size. Right? Sorry, here mistake written. Element has less size. Positive ion of element. Okay, correct. Negative ion of an element has. No mistake. So here, chlorine atom size is smaller comparing with chlorine ion. So chlorine forms negative ion because of adding one element, electron into the outermost. So 11, 17 protons, 29 became great. So when the electron charge cloud becomes greater than nuclear charge, automatically what happens? Size increases. So here, which has greater size? Atom or the ion? Atom or the ion? Here, atom has smaller size, right? Ion has greater size. So look at when the positive ion formed, its size is decreasing. When the negative ion is formed, the size is increasing. This you need to understand. So time completed. Join immediately in the next meeting. We will discuss there.